Now we will discuss about double refraction. Let's discuss about double refraction. But before we discuss about double refraction, we will see the crystal which give rise to double refraction. Double refraction is a phenomenon where an incident light give rise to two refracted light. An incident light, when it falls on doubly refracting crystal, it's a very special kind of crystal called doubly refracting crystal. When it falls on doubly refracting crystal, it gives rise to two refracted rays. One of the refracted ray is called ordinary ray and other refracted ray is called extraordinary ray. We call one of the ray ordinary because they are following all the laws of refraction, while the other ray do not follow the law of refraction. That's why they are called extraordinary ray. I'll go into detail of double refraction, but before that, let's first study what is double refraction crystal. What are double refraction crystal? A crystal which gives rise to phenomena of double refraction is called double refraction crystal. Let's take the example of calcite. Calcite is an example of a double refraction crystal. When a light is falling on the calcite, it will break into two refracted rays. Light is falling on calcite, it will break into two refracted rays. Calcite is basically CaCO3. The chemical formula is CaCO3. It's also known as Iceland spar. It's colorless crystal. It is colorless. It's colorless crystal, and unit cell is rhombohedral. Each face of the crystal is a parallelogram having adjacent angles 102 degree and 78 degree. I'll draw the unit cell. It will be very clear. I'll draw the unit cell of the calcite. The calcite is, I'll draw rhombohedral. This is the unit cell. Right? One of the corner is called blunt corner. We call one of the corners blunt corner. Blunt corner is the corner at which we define you'll have a blunt corner in the calcite crystal. The vertex at which all the faces meeting there makes an obtuse angle, meaning this angle, and this angle, all the three angles are obtuse. They are obtuse angles. All the three angles are obtuse. Now, from this blunt corner, we'll have two blunt corner. If this is a blunt corner, this will also be a blunt corner. Now you draw a line passing through this blunt corner and making equal angle with all the faces. You draw a line passing through this blunt corner and making equal angle with the three faces. You draw a line passing through the blunt corner and making equal angle with all the three faces. The direction shown by this line is called optic axis. So I write the definition. That's extremely important. The direction shown by a line. So the direction shown by a line passing through the blunt corner and making equal angle with the faces is called optic axis. So optic axis is not a line but a direction. Optic axis is not a line but a direction, right? The action shown by a line passing through the blunt corner and making equal angle with the faces is called optic axis. We call it optic axis, right? Now do one thing, is draw a plane passing through this line and perpendicular to the pair of opposite faces. You draw a plane passing through this line and perpendicular to this face and this face. Such a plane can be drawn as, this is the plane. I have drawn this plane. There is a plane passing through this line and perpendicular to the pair of opposite faces. I will shade it. So this is a shaded plane. This is passing through the line, this is containing the line and perpendicular to the pair of opposite faces. This is passing through, this is containing the line. I have drawn a plane containing this line and perpendicular to the pair of opposite faces. This plane is called principal section. We call it principal section. We call this plane as principal section. If let me draw a plane which is parallel to this shaded plane. Let us draw a plane which is parallel to the shaded plane, right? Something like this. Let's draw a plane which is parallel to the shaded plane, that is a green one, green plane. So I have drawn this plane, this is parallel to the shaded plane, this is parallel to the shaded plane. So this plane will also be called principal section. In fact, principal section is a plane containing the optic axis and perpendicular to the pair of opposite faces. And since optic axis is not a line but a direction, optic axis is not a line but a direction, so even this plane, red one, is also containing this direction shown by this line. See, the green one is containing the line itself, so it contains the direction also. But the red one is containing not the line but the direction shown by the line. So I can say even red one is also containing the optic axis. So that's also called principal section. I can define principal section as, these terms are very important. Principal section is plane containing the optic axis and perpendicular to pair of opposite faces is called principal section. We call it principal section. We call it principal section. So any plane which is parallel to the shaded plane is also a principal section. Any plane which is parallel to the principal section will also be the, any plane which is parallel to the shaded plane will also be the principal section, right? Now, what's the importance of principal section? Why principal section is so important? I'll tell you why principal sections are so important. See, when you have an unpolarized light falling on the doubly refracting crystal like calcite, when you have unpolarized light falling like this, say you have unpolarized light falling over here, unpolarized light beam falling on the calcite crystal, wherever it falls I can draw a principal section. Wherever it falls I can draw a principal section. Like it has fallen here, I have drawn the principal section. Now it will get split into two light. One is called ordinary, other is called extraordinary. One we call it ordinary, other is called extraordinary. The ordinary light will be having all the vibration parallel to the principal section. Suppose this is ordinary, right? Sorry, this is extraordinary. Extraordinary light is, extraordinary light is having all the vibration, all the field vibration parallel to the principal section. This is extraordinary wave, or simply called E wave. We call E wave. Don't write it so much big. It is called E wave, extraordinary wave. And ordinary light is having all the vibration, field vibration perpendicular to principal section. That's called O wave. So both are plane polarized. E wave has got all the vibration parallel to the principal section, whereas O wave has got all the vibration perpendicular to principal section. Wherever it falls, we just draw principal section. At any point where it falls, we just draw principal section. It was split into two waves, whereas E wave, both are plane polarized. This is unpolarized. This is unpolarized. So unpolarized light will convert into, will split into two plane polarized light, with one having all the vibration parallel to principal section, other having all the vibration perpendicular to principal section, other having all the vibration perpendicular to the principal section. Alright. So this is unpolarized wave converting into two plane polarized wave. So that's called double refraction. Right. We call it O wave because it follows all the laws of refraction. E wave do not follow the laws of refraction. E wave do not follow the laws of refraction. Alright. It travels with different velocity in different direction. Alright. So based on the number of optic axis, we classify the doubly refracting crystal into two types. You have doubly refracting crystal can be classified into, one is called uniaxial, other is called biaxial. In uniaxial, you have just one optic axis, and the examples are calcite, tourmaline, and quartz. Whereas biaxial, you have two optic axes. The examples are topaz and aragonite. Examples are topaz and aragonite. Now I'll discuss with you about a device which is used to produce a plane polarized light. That's called nickel prism. Nickel prism is a device made up of calcite. Let's discuss nickel prism. See, nickel prism is an optical device made of calcite crystal for producing and analyzing plane polarized light. Right. Let me draw the principal section of calcite crystal. This is principal section of calcite crystal. This is 71 degree and this is 109 degree. Right. Again this is 71, this is 109. Now we file the crystal from this side. We file it from this side. When you file it, it becomes, when you do the filing, this angle turns out to be 68. This angle becomes 68 and this becomes 112. This is 68 degree and this is 112 degree. Similarly, this is also 112 and this is 68 degree. Now you do one thing, you cut this crystal. Okay, cut over here. Cut this crystal, and now you add this crystal and use a very special gum over here, and that's called Canada balsam. Cut this crystal and use a gum called Canada balsam to add them once again. Right, to add them you use the gum called Canada balsam. Alright. Now the light which is falling, which is incident on the calcite crystal, like this is light which is falling on it. It will break into two light. It will break into ordinary and extraordinary. Say this is extraordinary and say this is ordinary. So what will happen is, see, it will break into ordinary and extraordinary. Say this is ordinary having all the variation perpendicular to principal section. This is ordinary extraordinary having all the variation parallel to principal section. Now the refractive index of calcite, for ordinary is, for ordinary light, that mu O is 1.658, and for E wave it is 1.486. Means E wave travel faster compared to O wave in the calcite crystal, right? The velocity become equal when the direction of propagation lies along the optic axis. So your E wave and O wave, they have different refractance. The same material, the crystal presents different refractive index for O wave and E wave. Mu O is 1.658 and mu E is 1.486. Now you can see the refractive index of Canada balsam. The refractive index of Canada balsam is, it is 1.55. The refractive index of Canada balsam is 1.55. So this is your E wave and this is your O wave. Now what we do is we set the angle. In such a way. See, this angle is here. The light is made to fall at such an angle that this incident angle theta I becomes more than theta C. What is theta C? Theta C is the critical angle. Theta C is sine inverse, that will be sine inverse 1.55 upon 1.658. So if this theta I becomes more than sine inverse 1.55 upon 1.658, then this ordinary light will undergo a total internal reflection. This light will undergo a total internal reflection. It will come like this. Whereas an ordinary wave which is having a refractive index in this side is 1.486, say 1.55, so it will continue to move in the same direction in the crystal only, right? So it will go like this. It won't suffer a total internal reflection, whereas ordinary wave you can see it suffers a total internal reflection. It will suffer a total internal reflection, right? So you find that O wave comes this way and E wave passes through the whole crystal and come out this side. So in this way it is a device from where I can generate O wave and E wave, and in the air both are same, both are like plane polarized waves. So I can generate a plane polarized wave using a nickel prism. So nickel prism behaves like a polarizer. It polarizes unpolarized light. From unpolarized light it is producing a plane polarized light. From unpolarized light it is producing a plane polarized light. So it is behaving like a what we call polarizer.